tutorial, you will learn the basics of numerically controlled oscillators and how they are used in FPGAs for digital signal processing. In part 1, a single NCO will be instantiated in a live FPGA to generate a fixed frequency sine wave. Next, you will learn how to use SignalTap, Altera's free embedded logic analysis tool. Finally, you will learn how to analyze signals exported from SignalTap to Octave, the open source alternative to MATLAB. Now bear with me, this first tutorial is lengthy and a bit dry, as it sets up the foundations for tool installation and usage. The real fun starts with the introduction of modulation techniques, as well as the Arduino and DAC integration, which will be explored in subsequent labs of the NCO series. So with that, let's get started. Today we're going to discuss the digital signal processing capabilities of the Amani F2 FPGA Sheild for the Arduino. And specifically we're going to talk about the usage of NCOs, otherwise known as numerically controlled oscillators, and their application in areas such as software-defined radio, etc. So the first thing you'll want to do is go to modulesurf.net, go to Amani projects, and download the Amani DSP _NCO zip file from that website. Go ahead and unzip the project into your directory of choice. Okay, now that you've unpacked the Amani DSP NCO project directory onto your desktop, we're going to go ahead and open Quartus 2. Hopefully by now you've downloaded your free version of Quartus 2 made available by Altera. If not, and you need help doing so, go ahead and go over to modulesurf.net, click on Tutorials, Altera Quartus 2 installation tutorial, and there is a link that will go ahead and take you over to Altera's Quartus 2 Web Edition software. And again, this is free for users to enjoy the free cores available by Altera and to suss out the software and do basic development. So for the beginning user, which the Amani F2 is intended for, Quartus 2 Web Edition will be pretty much the only version of the software that that user will need. Also required for this laboratory is Octave, which is the open source version of MATLAB. That is available at gnu.org. Okay, so now that we have Quartus 2 installed on our machine, let's go ahead and open the existing DSP project, Amani _DSP. So over in the hierarchy you'll see Amani _DSP, double click that, and the basic block diagram file has opened. Now you're going to see a circuit there that we're not going to use in the beginning here. This is the something we'll see at the end of the laboratory. So go ahead and delete all of that. Now what we're going to do is we're going to open our first core, which will be an NCO core that I already generated for you. It's a basic 16-bit NCO. So you go ahead and click on Symbol Tool. Click on Project, and you'll see an NCO _16, and the block symbol file appears in the window pane on the right. So go ahead and click OK. Let's go ahead and look at the inputs and outputs. So at the very top you'll see this vector phi _inc_i 15 down to 0. So basically what this is this is the phase incrementer input to this NCO. Essentially what you need to know for this particular core is this is what sets the actual frequency of the core. Next we have the clock input. We have the reset and the clock enable. On the output we have the F sine underscore O, which basically means this is the sinusoid output, 15 down to 0, so that's a 16-bit parallel bus that is useful for example, feeding forward to a DAC that has a parallel bus interface. That's one way you can drive actual hardware. You can also feed this forward to a SPI DAC transactor that I will make available at modulesurf.net, which is another way we can drive hardware. Or you can take the NCO output of this particular core and feed it forward to other parts of your design internal to the FPGA of the Amani F2. Let's go ahead and connect pins to this core, and we're going to feed it to the actual inputs and outputs of the F2. So click on the symbol tool icon, go to the libraries, primitives, pin, and we're going to use an input pin. Place that there, and let's go ahead and use an output pin as well. So for the purposes of this laboratory, we're only going to use the Amani F2 by itself. We're not going to use external hardware except for the JTAG programmer. In later labs we will connect to external hardware such as D to A's and A to D's. However, we just want to give you a basic introduction to some of the cores, DSP cores that are made available to you from Altera. So why we're connecting pins at this point in time is we want to use the signal tap logic analyzer. That's also a feature of Quartus 2, and it will actually connect to those pins and give you measurements of activity on those pins, and we'll get to that in a few minutes. So the output pin, we're going to connect directly to the sinusoidal output, and you're going to notice that it created a bus instead of a single wire. That's a single wire, and that's a bus. So we need to make sure that Quartus 2 understands that this is a bus and that the pin is actually connecting 16 output pins and not just one. So we set the net name to NCO underscore O, and then we set the vector width to 16. So we say 15 down to 0 as such. And then for the inputs, we're just going to go ahead and connect the clock only. And you see here it creates a single wire. I'm going to call that clock 64. So for the extent of your lab, if you've purchased an Amani F2 in December of 2012 or after, you have a board that has a 64 megahertz oscillator on board. The board that I will be using today is a 100 megahertz oscillator. That's one of the beta versions. It turns out that on the Amani F2, you can actually use a clock manager or a PLL to change the frequency from 64 to a higher frequency if desired. So for example, if you actually wanted to connect to high bandwidth DAC and create an FM modulator, for example, which we're going to do a little bit later in this lab, and you wanted it to be centered around 100 megahertz, you would probably want to sample at least the Nyquist frequency, which would be about 200 megahertz. So you would create a PLL or a digital clock manager for 200 megahertz. But for the extent of this lab, we're going to keep it simple, and we're going to use the for you guys the 64 megahertz oscillator. So we still have to take care of the phase increment value, as well as the reset _n and the clock enable. So for these two, we're just basically going to tie reset and clock enable to logic high. So we're just going to say VCC we're going to rotate it, and we're going to do so. So typically in industry, you're not going to use the block symbol and schematic capture method to do FPGA development. You're typically not even going to open the Quartus 2 tool itself. You're going to use some sort of Perl script and basically use the synthesis, run the synthesis tool externally via scripts. But for the beginner and for hobbyists, this is a pretty straightforward way of doing designing a system on the F2. So now we're going to take care of the phase increment input. So for this first part of the lab, we are just going to use a set frequency. So what I've done is I've generated a core under the project file called coefficient _16. And so for the new user, these block symbol files can be double-clicked and examined. And so what you're going to find inside of the coefficient _16.v file is the Verilog that drives this particular logic file or core. And basically what I've done here is I've set up a 16-bit vector called coefficient output, and it's a hexadecimal value of 1024. And so that actually translates, if you read the NCO, let's go ahead and open up Altera NCO core. That actually sets the output frequency of this particular NCO core. And for this application, we're setting a phase incrementer value to 1024, which translates, which translates to 4132. So 4132 times the clock frequency, F clock. So if in my particular case, it's going to be 100 megahertz. In your particular case, it will be 64 megahertz. Given that this is a 16-bit core, we're going to go 2 to the 16. And so we should expect an output frequency of 6.3 megahertz when we use the coefficient of hexadecimal 1024. So we're just going to go ahead and hook that up to the NCO 16. And again, we're going to leave this particular output valid flag open. So now we have the schematic captured, we're going to hit save. Okay. We want to run the pin planner first. But before we do that, we're going to want to compile the project. Right off the bat, you're going to see this pop-up window saying compilation was successful, 22 warnings. At this particular stage, I would not worry about the warnings that are being generated. So let's go to the pin planner, and you're going to see the following pins: 64, and then NCO underscore O, 15 down to 0. So if you remember, the NCO underscore O are for use for the signal tap logic analyzer. So we're not going to connect them to the real world. However, we're going to connect clock 64 to the actual onboard oscillator. For you guys it's 64 megahertz, for me it's 100. And so we know that to be pin 88 because of the pin map file available at Amani64.com. So the column of interest for Amani F2 users is this particular one. So we have a general purpose clock 0, which is pin 88. We have one LED available to us for number 112. And then I break out the rest of the pins accordingly. So PB, PD, and PC are the familiar Arduino pins, header pins. And then we have dock A and dock B, which are this is dock A, this is dock B. These are the standard Digilant PMOD headers. And then we have DBA and DBB, which are these two particular header areas. And so you'll notice that DBA and DBB have 4 PMOD headers as well. So those are left unpopulated for the end user to populate however they like. You can go ahead and look at the design package at Amani64.com to understand how to better use that. So going back to the pin planner, we know that we want to connect pin 88 to clock 64. And so now typically what you would do is you would just click in the box. You can either use the drop down menu, or you can just type in 88 and you'll get pin 88. The funny thing about the pin planner tools, you don't have to save. You can just go ahead and X out, and that will have already saved. So now what we want to do is set up our signal tap configuration file. So go to Tools, Signal Tap to Logic Analyzer, and the following window will appear. What you're about to see is a legacy plot that you're not supposed to see yet. You're ruining the surprise. So go to the Setup tab. Let's go ahead and delete everything. The first thing you're going to want to do, now this has already been configured for you, but let's just go ahead and go through the exercise anyway, is in the signal configuration box, you want your clock to be clock 64. So this particular window will pop up, drop down and say pins all list, clock 64, OK. There you go. Sample depth for the scope of this project, we're just going to make it 1K. For JTAG configuration hardware, so this is what's going to program the FPGA on the Amani F2, as well as the single tap logic analyzer will speak through the pick JTAG tool through the JTAG interface on the Amani F2 and read the logic levels of the various pins internal to the FPGA. So you're going to go ahead and use the USB blaster. There's a tutorial at the website on how to install the JTAG programmer. And then we'll go back to this particular box in a minute. So we want to look at, we basically want to bring up the signals that we want to monitor. So you double click to add the nodes. Again, let's just use pins :all list. So you cannot monitor the clock because that's what's being used to trigger the nodes. So in this particular case, the only one to monitor now is the NCO_out. So just go ahead and click the vector at the top, and these will be broken out for you. Click the I guess the greater than symbol to put that over here in the selected node pane. Click OK, and you'll see it here. And if you click the plus, you'll see it broken out. You can click plus again to minimize that. So we want to save this configuration. So in this particular case, we're going to save, we're going to overwrite the Amani_DSP_SIGTAP STP file. Just go ahead and say yes. Now that has been saved, X out, and now we will recompile. So that what the changes that we're recompiling now, resynthesizing, are the signal tap changes as well as the pin assignments. Let's go ahead and open the signal tap tool once again. And we're going to click this icon, the program device icon next to the SRAM object file manager. So make sure that the correct programming file, the soft file, is selected. And it is in the correct project directory. So Amani_DSP_time_limited.SOAP. So what does time limited mean? That means that that Quartus 2 is allowing us to evaluate this particular core, which is the NCO core. So unfortunately, in this particular case, we cannot make this a core that will be field installable unless we purchase this particular core from Altera. However, that being said, being hobbyists and beginners, if you actually want to use this in the field, there are cores available at websites such as opencores.org, where you can download all sorts of digital signal processing cores. So let's go ahead and click the icon, and you're going to be presented with this this radial that says, or this window that says, this is a time-limited core. This is basically what I explained to you guys. And just click OK. And we've now successfully programmed the FPGA. So let's go ahead and run one sample. Alright, so you see this red bar to the right of the NCO_O. So if we start to zoom in, we can see 16-bit hexadecimal values. At each of the clock sample points. So that's fine and all. It's if you can read hexadecimal and understand exactly what you're seeing, and you know 2's complement, and you understand signed math, then by all means this is meaningful to you. For the rest of us, we need to go to bus display format and view it in, for example, signed decimal and signed magnitude. So now we can read the NCO output values in decimal format with their particular sign in front of them. However, one of the nice features is we can actually view it as a signed line chart. And now we see the actual sinusoid output of the NCO. And probably more accurate is the signed bar chart, signed bar chart. Okay, so that in and of itself is pretty useful, and we can actually free run that. However, we can take it a step further and use Octave to perform analysis on this particular NCO output. So let's take the bus display the bus in the signed decimal output again. Then we're going to go to File, Export, and we're going to export this file in the Octave directory as Amani _ NCO 16. And it's important to maintain that file name because the Octave scripts that I've generated for you queue off of that. Hit open, OK, and it says successfully exported data to file. OK. Now let's go ahead and open Octave. And let's navigate to our project directory and to the Octave directory. And we want to go ahead and run the Amani _ NCO16.m file. So all you have to do is just type Amani _ NCO16 and the following window will pop up. So here again we see the output sinusoid of the NCO core as well as the NCO spectrum. First of all, let's just go ahead and measure the period of this particular sinusoid. So 43.7 and 59.7. (16 clock ticks). Okay. So in my particular case, it is 16 divided by 100 megahertz. Which gives us a frequency of 6.25 megahertz. So let's go ahead and sanity check that. Coefficient value was 1024, 4132 times 106. For a 16-bit NCO, 6.3 megahertz. So we're slightly off in our calculation. We know the period to be on the order of 6.25, or I'm sorry, the frequency of this output is 6.25 megahertz. So let's go ahead and look at the spectral output. I'm going to go ahead and shove the image frequency, move everything down to 0. So here we see the FFT is reporting that this particular tone is visible in in bin 65. So what we do is we take the sample frequency, or the clock frequency, in our particular case 100 megahertz, divide that by 2, which is 50 megahertz for the Nyquist frequency. And then we go ahead and divide that again by the number of bins that we use for the FFT. So here we used an FFT, a 1024 point FFT, but because we're only using the real portion of the FFT, we're only going to use the 512. So you divide this 50 megahertz by 512. Okay, so what we're seeing is 97.7 kilohertz per bin. So again, we see that this this tone shows up in bin approximately bin 65. So we multiply this by 65, and here we are again at 6.34 megahertz. So that's more on the order of what the NCO core was generating, whereas the period up above, I probably was slightly off with my calculation there. So that's how you can integrate Octave with Altera's signal tap tool. And so that's a basic NCO core, and that's pretty neat. And we can use that to connect to the real world and use a DAC and generate signaling that way. But what are some other techniques that we can apply to the NCO to make it more meaningful to real world applications?